Hello and welcome to the eTech podcast with me, your host, Ryan Maughan. I have been involved in the development of electrified vehicles and machines since 2005 as an engineer and a business leader. This podcast is the product of my passion for electric and autonomous vehicle technology. I'm here to share knowledge from some of the world's leading experts, as well as my own insights. Join me as we accelerate the transition to cleaner, safer and smarter vehicles and grow the industry around the world. So I'm here today at Transense Technologies with Victor Kalinin, and we're going to talk about surface acoustic wave sensors and torque measurement. The first thing, though, that I do need to say is, although this podcast hasn't been sponsored by Transense, I do work with Transense and I'm paid by them in an advisory capacity to help them with their business. But just for today, Victor's agreed to give me some of his time, and we're going to talk about him and his history and background and the kind of really interesting things that they do at Transense with this unique sensor technology. So, welcome, Victor.
Thank you. Thank you for the introduction.
Yeah, no problem. I wonder if we could just start with your background. So, tell us where you're from.
Right. Well, I've been working as a chief scientist and technologies director at Transense Technologies for 20 years. Before that, I was a university lecturer and a researcher in the field of RF engineering, radio physics, and physics of surface acoustic waves for 22 years, first in Moscow and then in Oxford. I have to say that I always knew that I would become a physicist or a scientist and an engineer.
Yeah.
Always. Starting probably from the time when I was 6 years old kid.
And what was it that kind of triggered that?
Yes, I can remember that time very well. Very well. And the reason for that is quite simple. This is mostly the influence of my family, because both of my parents were engineers, and my elder brother was also a scientist and an engineer. Besides, I probably read too much science fiction when I was a boy.
Okay.
Definitely, I preferred to read science fiction than go to music lessons.
Right. Okay. Yeah. Yeah. I think a few of our listeners can probably relate to that. Yeah.
Yes. But I read a proper hard science fiction, not fantasy about dragons, wizards, and warriors with swords. And as a result, I became an engineer, and I started my engineering career in 1978 when I got my master's degree from the university, and then I became a university lecturer in 1983 after getting my PhD.
And that was, you were in Russia still at that point?
Yes, I was in Moscow. I was working and studying at one of Moscow technical universities.
Right.
The biggest question, and I probably can't answer it for myself even now, is why I decided to move from academia to industry after 22 years of my academic career.
Yes, yeah.
It's not an easy question. Perhaps I just wanted to be a bit closer to real world.
Yeah.
And do some things that could be a bit more practical and more useful to people.
And when you moved from Russia to the UK, was that you were still in academia at that point?
Yes,
yeah.
Yes. Basically what happened, I got a research position at the University of Oxford.
Okay.
But that was quite a short employment.
Yeah.
But during that, I was persuaded to take part in, basically to try and apply for a permanent position.
Yeah.
At Oxford Brookes.
Okay, yeah.
So I got it, and as a result, I moved from Moscow to Oxford.
Wow, okay.
That's what happened. So after that, I worked as a senior lecturer at Oxford Brookes for several years, for 6 years in general. And at the same time, I was a consultant for Transense Technologies for a couple of years.
Okay.
And at some point, they offered me a position of a chief scientist.
Ah, okay. Yeah. So they lured you out of academia into the real world.
Yes, that's right. That's what happened.
Yeah.
After some resistance, I accepted the position.
They wore you down. After 2
Yes.
years, they eventually convinced you.
Yes, yes.
So was your academic sort of life, was that focused around RF devices or SAW technologies? Was that something you were deep into?
Well, not quite, because I, for 1 year, from 1986 to 1987, I worked at the University of Oxford with Professor Laszlo Solyma, and we did some research on photorefractive materials in application to optical signal processing, phase-front conjugation, things like that.
Okay.
So that I continued doing this research when I went back to Moscow, and then when I came to Oxford as well.
Okay.
So we published a number of papers on this subject, on physics of photorefractive materials. But at the same time, somehow Transense people learned that I was working on SAW devices in the past.
Right.
I did my PhD on surface acoustic wave physics and design of the devices. So they asked me to do some design for them, and that's what I did. That's how I became consultant for Transense.
Okay. Yeah.
Gradually, I moved from the field of optical signal processing back to surface acoustic wave devices.
Yeah.
And I also did some work on just design of RF circuits back in Moscow. So it was quite natural to me to move to SAW sensing.
Because it's very close linkage there with the RF side. And
yes, absolutely.
And maybe probably a good segue into what is it that Transense do? So as a company, what are you engaged with?
Well, Transense was quite an attractive place to work, actually, because for me it wasn't much different from the university research group, because it was a small company with a very special, creative and inspiring atmosphere, which is quite characteristic for research and development enterprises.
So nice being sort of working right in amongst the technology, not too kind of abstract.
Yes.
Yeah.
Yes, that's right. The company itself was founded in 1991 by 2 engineers, entrepreneurs,
okay,
and 1 financial journalist.
Okay.
And the company became especially active in 1999 when it went public.
Right. Yeah. Yeah. So Transense is a PLC.
Yes, it's a PLC.
You, for anyone interested, I'll put some links in the show notes for you to sort of check out, where you can find out more about it. But it is a publicly traded company. Yeah. Okay.
Yeah. And the main idea of the company was to develop IP in the field of surface acoustic wave sensors for automotive industry, in particular for electrical power assisted steering, EPAS, and tire pressure monitoring system, TPMS.
Okay. Right.
Well, the question one can immediately ask is why surface acoustic wave sensors?
Yeah.
What is special about surface acoustic waves?
Yeah.
Well, actually, intensive development of
there's a first of a question of what is a surface acoustic wave?
Yes. I'll try to answer it in one sentence.
Okay.
The intensive development of surface acoustic wave devices began in early 1970s, after invention of a so-called interdigital transducer. It's a thin-film microelectronic device that could convert electrical radio frequency signals into surface acoustic waves in a very, very efficient way. What is the surface acoustic wave? It basically looks like a sea wave, but it propagates not on the surface of a sea, but on the surface of a polished solid body.
Ah, okay, yeah. So we've got the interdigital transducer, which is like 2 combs basically, or you digits like your fingers,
yes.
And we're creating a wave which
Yeah.
on that. Okay.
Yes, due to the piezoelectric effect of the substrate, because the solid body which is used in SAW devices is usually a piezoelectric crystal.
Yeah. Yeah. Okay.
Okay, so that this wave runs along the surface of this crystal, and at this point we should bear in mind that the velocity of acoustic wave in general, and surface acoustic wave as well, is 5 orders of magnitude smaller than the velocity of light.
Okay. Yeah.
So as a result, the wavelength is of a micron size,
Right.
and as a result, the dimensions of SAW devices are quite small.
Yes. Yeah.
Within 1 millimeter structure or 2 millimeter structure, you can achieve a very nice, very unique frequency response.
Yeah.
And you will never be able to achieve a similar frequency response using traditional electronic components like capacitors and inductors.
Yeah.
So these miniature, very stable and inexpensive devices quickly became a dominating technology in intermediate frequency filters,
Okay.
delay lines,
Okay.
and resonators.
Okay.
And you could find them in every TV set, in every transceiver,
Okay. Yeah.
and in every radar.
Yeah.
That's what started in the 70s.
Okay.
And later, in the 90s, surface acoustic wave technology became a dominating technology for RF radio frequency, front-end filters and duplexers for mobile phones and base stations.
Yeah. Yeah. And so using it as a sort of electronic component like that, as a filter device, it's essentially the same technology as you've got in your sensor devices.
Exactly. Yes, it's exactly. But it has become obvious back in 70s that the resonators based on surface acoustic waves and delay lines can also be used as temperature and strain sensors. It was known for quite a long time.
Possibly by accident of noticing they're not quite doing the job you expect when they're under different physical conditions.
Yes, quite often this sensitivity to temperature and strain was regarded as a parasitic effect that people tried to avoid.
Yeah.
But also, quite a number of researchers did investigate the possibility of using them for sensing.
Yeah, yeah.
Well, this is why can they be used as sensors? Just simply because the physical dimensions of the SAW substrate, as well as the SAW velocity, happens to depend both on temperature and on strain. However, SAW strain and temperature sensors didn't find any noticeable applications in the real world till the middle of the 90s.
Why do you think that was?
Well, I think, and I'm sure I'm right, it was very difficult for them to compete with significantly less expensive traditional temperature and strain sensors.
Okay.
In their wired form, when a surface acoustic wave sensing element is hardwired to the active electronic circuitry that is necessary for the sensor, the advantages of using SAW devices as sensors, due to their high stability or better resolution, often just don't outweigh their increased cost.
Right. Okay.
That's the situation with wired SAW sensors.
And is that because you've got this sort of, I guess, fairly inexpensive interdigital sensing unit, but then to make that work, you've got quite a bit of electronics sitting behind it.
Exactly. You need to make it a part of an oscillator, for instance.
Yeah.
You need to include this device, being it a delay line or a resonator, into a feedback loop of the oscillator. And then you also need to measure the frequency of this oscillator.
Yeah. Yeah.
And so that there is quite a bit of electronics which is involved in the SAW sensor, even if it's just a wired device.
And I can imagine back in the day, actually doing that kind of thing at the right frequency was pretty difficult, you know.
Yes, it wasn't straightforward. That's right. It wasn't.
Yeah. Whereas sort of more modern microprocessors and signal processing technology probably has made that much more straightforward.
You're absolutely right.
Okay.
Only by the middle of 90s, the progress in CMOS RF circuits, integrated circuits, I mean, and in microcontrollers and in digital signal processors, allowed to reduce the cost of intelligent transceivers to the level that sort of renewed the interest in surface acoustic wave strain and temperature sensors.
Yeah.
Why did it happen? Well, first of all, everything went wireless in the 90s.
Yeah.
Wireless phones, wireless keyboards or mice for computers, even wireless toothbrushes.
Yeah.
Absolutely everything went wireless. So temperature and strain sensors also tried to become wireless.
Yeah.
But yes, you can connect a telemetry transmitter to a traditional temperature or strain sensing element like strain gauge.
Yeah.
But in this case, you will have to provide a DC power source for that transmitter.
And that's so it's sort of important, I guess, point that the common method of providing a wireless torque sensor on a shaft involves putting quite a lot of electronics on the shaft.
Yes.
With normally some sort of battery power or inductive coupling to transmit power on the shaft.
Or energy harvester.
Yeah, and you've got then electronics on the shaft that are transmitting a signal off the shaft in the same way that a phone would transmit a signal. But the sort of differentiator with the SAW technology is actually all the things that are on the shaft are passive.
Yes, absolutely.
The electronics sit off the shaft.
Yes, exactly. If you use a strain gauge connected to the telemetry transmitter, then the whole device will probably weigh tenths of grams, or not even, or maybe even hundreds of grams, while the SAW device itself weighs only milligrams.
Yeah.
And besides, it's totally passive device. It doesn't require any DC source for its operation.
Yeah.
And it's very well suited for wireless interrogation.
Yeah.
Especially if it works within the frequency range from 400 megahertz up to 5 gigahertz.
Oh wow, okay. Yeah. One of the challenges with a traditional, and I know this from the past, from my experience of trying to make strain gauges work on electric motors and things, they don't really like background noise because of how a conventional strain gauge works. How does a SAW sensor react to background noise? You know, I'm kind of thinking, is it a challenge with a SAW sensor with background?
Well, to much less extent than for the strain gauge, because the strain, when you use a strain gauge, you rely on measuring its resistance. Yeah, basically, because and in this case, you need to perform amplitude measurement. Yeah, and obviously, any noise at any frequency range will contribute to the random errors. Of the measured strain. The SAW device is a bit different from that. How do we interrogate passive SAW devices wirelessly? Let's consider a sensing element that is based on a SAW resonator. We actually prefer to use SAW resonators rather than delay lines because they have low insertion loss at radio frequencies and higher Q factor.
So you lost me now. What do you mean by insertion loss?
Insertion loss. Yeah. Well, you can apply an RF signal to excite the SAW device, and then you can measure the response of the SAW device. So then you divide the amplitude of the SAW response by the amplitude of the excitation signal, and that ratio is obviously less than unity. Yeah. And it characterizes the insertion loss. Okay. Usually it's expressed in decibels.
Okay. So does that mean you basically don't need a lot of power because you're getting quite a good signal back?
Compared to the delay lines, that's true. Resonators have lower insertion loss, and at the same time, they have higher quality factor, Q factor.
Okay.
And it turns out that the Q factor determines the potentially achievable resolution in case of wireless interrogation.
Okay.
So the higher the Q factor, the better the resolution of the sensing system.
And what is so quality factor? What does it mean in practical?
The quality factor determines the length of the response of the device after its excitation by a very, very short pulse. We call it delta function or Dirac's function.
Okay.
So that how long the response is after you kick the device and excite it.
Right, okay.
The longer the response, the better the resolution.
Okay. I guess the easier it is to measure and things like that. Yeah, okay.
Yeah. So to measure the SAW resonant frequency in a remote way, we use an electronic interrogation device that we call a reader, and this device sends periodically a very short RF interrogation pulse. This pulse is picked up by the sensor antenna, a simple antenna connected to the passive sensing element with a resonator. It excites the resonator, and the resonator starts ringing. And this ringing continues even after the end of the interrogation pulse for a long time, which is determined by the Q factor.
Okay.
And then this electric oscillation is being retransmitted by the same sensor antenna back to the reader antenna.
Right.
The reader's receiver picks up this signal and analyzes it, finds the frequency of the ringing, which is the same as the resonant frequency, and then it calculates torque, temperature, strain. That's how it works. So the difference from the strain gauge is that we measure the frequency rather than measuring amplitude.
Okay. So you're less, basically background noise doesn't matter.
Well, at least it still matters, but to a lesser extent than for purely amplitude measurements.
Okay. Easier to filter out. Yeah. What about things like electromagnetic fields?
Well, it's a good question. Obviously, the reader's receiver has certain front-end circuits, front-end filter, that limits the bandwidth, so that if there is a signal, interfering signal outside this bandwidth, then it's suppressed by the front-end filter and subsequent circuitry of the receiver. But if the interference happens to be within the working, operating frequency range of the sensor, then we are in trouble.
Okay, yeah.
So the only way how to sort of mitigate this is to perform the measurement of the noise before launching the interrogation pulse.
Okay.
And
so
then wait until
kick, listen again.
Listen before interrogate.
Yeah, and I guess
strategy.
You can do that cycle many, many times a second.
Yes, that's right. Well,
another question just popped in my head. Sorry to hit your flow, but what about? I guess if you held like a regular magnet, sort of magnetic field, because it's the actual sensor element, the interdigital sensor. That's there's no ferrous materials in that or anything. It's not going to see that magnetic field, will it? That shouldn't affect it at all.
No, it's not sensitive to magnetic fields at all.
Yeah.
Unlike magnetostrictive sensors.
Right. Okay. Yeah.
It's much less. Well, it's not much less. It's totally insensitive to stray magnetic fields, and for that reason, one of the advantages of SAW sensors is that they can be used quite safely near powerful electric motors. Power electronic circuitry, things like that.
Yeah. Because it's always a challenge in a design of a motor and electronic system, because you do have strong magnetic fields. All over the place in in the cabling, in the motor itself, in the inverter unit, and quite often you're measuring those magnetic fields to get estimate or calculate the performance of the machine, or the system. But the components you're using have to be able to withstand exposure to those fields, which can be quite a challenge for some with some sensors.
Yes, that's right.
Yeah.
The reader is not a simple electronic device. Back in the 80s, it would probably occupy the size of a good desk drawer.
Desk drawer?
Desk drawer, and it would cost something like several, well, maybe even tens of thousands of pounds.
Okay, right.
Well, it's basically a radar. It's a very specialized spectrum analyzer.
Wow.
So
okay.
it's not it's
nothing trivial.
No.
Yeah.
No. But due to the advances in the microelectronics, the situation is absolutely different now.
Yeah.
At Transense, we have developed an application-specific radio frequency integrated circuit, RF ASIC,
right?
That, together with the off-the-shelf digital signal processor, does all the work of the reader.
Okay.
And the reader now can fit within a matchbox. Okay. And its cost is quite acceptable for high-volume automotive applications.
Wow. So that, it's quite, obviously electronics development, it's driven so many things, but it's quite a sort of graphic illustration that you've gone from something that was physically the size of a desk drawer, so maybe 50 centimeters by 30 by 15 or something, and that basically doing exactly the same job, but through the application in an ASIC has been able to be shrunk down with a few other components to something the size of a matchbox. That's quite phenomenal, really. Did it take a long time to develop that?
Several years.
Okay.
Several years.
And I guess so your background at that point and mixed experience with the RF electronics and with the ASICs must have come in really been very, very valuable to that development.
Yes. What happened? First of all, we did quite an extensive simulation at a system level of the entire reader. After that, we designed and built a prototype on the discrete components, of the shelf components. And only after that, we could specify every single component of this reader and then do the development together with a company specializing in automotive electronic integrated circuits. And now they are producing this RF ASIC chip for us and our licensees.
Okay. And it's quite interesting. To be honest, I hadn't realized, I probably should have, the fact that you start from the start, it's always been about going into the automotive sector. So, because the requirements for automotive are quite demanding in terms of reliability and robustness and things like that. So, because you started there, actually it probably made life a bit more difficult initially to make something that was going to do what it needed to do. But now you've got something which is very a robust little product set.
Yes, I hope so. I think so.
Yeah. And you mentioned about making in volumes, because actually one of the sort of really interesting things about Transense is you have commercialized already in some applications. So
yes, that's right. I will mention these applications a bit later.
Okay.
I just want to say now that we can now do the wireless measurement of the resonant frequencies of the SAW resonator with the resolution better than 400 Hertz at the frequencies above 400 megahertz. And we can do this measurement within 150 microseconds. So this is not bad at all. But being able to measure this resonant frequency accurately, unfortunately, is not enough to measure strain and temperature. And the point is that the frequency of the saw resonator depends both on torque, both on strain and temperature.
Right, okay.
But what we want is to be able to measure independently strain and temperature.
So how do you sort of separate the two out?
We have developed the method that allows us to do the temperature compensated strain measurement and independent temperature measurement by using several different saw resonators within one single sensing element.
Okay, right.
And we also developed calibration methods for this sensing element.
Right.
And this is a part of the intellectual property portfolio of our company.
So you're able to look, presumably you look at the temperature, and then you're able to sort of take that value out of the combined measurement to compensate back over for that.
Yes, that's right. That's
okay.
the basic. Basically, this is correct.
Okay.
Although since we use resonators with a different design, they are affected by temperature and strain differently.
Yeah.
And this allows us to resolve both physical quantities independently.
And that's why, because when you look at the saw element, initially we described this interdigital sensor, but when you look at the sensor, that's not what you see. You kind of see this kind of it looks like when you blow it up, someone said to me it looked like a video character, but it's sort of a scattering of elements inside the sensor. There's quite a lot going on in there, and that's these multiple different saw units.
Well, obviously we can't compare complexity of our sensing elements with modern processes.
Yeah.
The number of elements is smaller.
Yeah.
We are talking about hundreds of elements.
Yeah.
Which you can find in the layout of our sensing elements.
Yeah.
Still not trivial design.
Yeah, and they're all, it's still totally, it's passive. We're creating those elements actually with a similar production method as you would make an ASIC or a semiconductor device, but you're effectively fabricating those elements at a micro scale in very, very thin materials. In that sort of fab type process.
Yes, the sizes of the elements are about 1 micron.
Wow.
And the number of elements, as I said, hundreds of various stripes, rectangles made of thin aluminium film.
Yeah.
And the thickness of this film should be very, very carefully controlled because we need to achieve good tolerances.
Yeah.
Rather tight tolerances on the resonant frequencies.
Yeah. Okay. Yeah, got it. Interesting.
That's the sensing element. Another part of the intellectual property portfolio of Transense is the patents that allow us to design sensor antennas and reader antennas that can be used on the shafts with diameters varying from 20 millimeters up to 420 millimeters.
That's a big shaft.
Yes, it's a big shaft.
Yeah. So covering, I know you mentioned initially the steering device, and you probably talk about that later, but a 400 mil shaft could be a very large propulsion system, a ship or something.
Yes. Yes, it can be, for instance, the output shaft of an big industrial gearbox.
Yeah.
One of the examples is the gearbox used on big wind turbines.
Okay, yeah. And these antennas are they're sort of quite clever, but in that they're quite simple.
They are pretty simple and not expensive at all.
Yeah.
They are based on, there are different designs that we used in the past. But many of them are made of a standard printed circuit board material, so-called FR4 or FR5.
Yeah. And you simply have an antenna on the rotating part and then another antenna for fairly close to it, held static.
For torque applications, we do use antennas that what we call near field antennas that are positioned relatively close to each other. The gap between the rotor part and the stator part is probably, between 1 millimeter and 20 millimeters.
Okay. So it doesn't have to be like a half mil gap. And I guess it doesn't really matter if that gap moves particularly?
To some extent, definitely it's much less sensitive to movement than the pickup coils of magnetostrictive sensors.
Right, okay.
We still need to make sure that the reader antenna doesn't get too close to the sensor antenna.
Right, yeah.
Because in this case, we will face quite noticeable rotational errors. The measured frequency will start depending on the rotation angle, which is an undesirable thing.
Yeah. So it actually pays. So you want them further apart, not too close together.
Yes, but to a certain extent, because since it's a near field antenna, if you move it too far away, the signal strength will be too small.
You lose the signal.
So that there is a certain range within for the sort of axial movement of those antennas.
That's really interesting, because it's a lot of times you think of, when you're designing a system with a rotating shaft, you want to allow for movement on the shaft and vibration and things like that, but it sounds like that shouldn't really be a problem here at all.
Well, it's much less of a problem for source sensors because, as I said before, we rely not on amplitude measurements, but on frequency measurements. And the fact that the signal becomes weaker doesn't matter to that extent. Well, clearly, when the signal is too weak, the random errors in the measured frequency will increase, but it doesn't affect the measured value itself.
See that? So it's always self-compensating. Okay.
Well, since our sensing element is well suited for strain measurement, we can also measure any physical quantity that can be converted into strain in the SAW substrate.
And that's where you come into torques.
That's right. But we also design, how do we convert the physical quantity into strain? Well, it depends on the physical quantity we measure. Yeah. For instance, to measure pressure, we developed a special metal package that deforms the source sensing element depending on the pressure applied.
Yeah.
This way we designed a pressure and temperature sensor for tire pressure monitoring system. And we also developed what we call an all-quartz package for the torque and temperature sensing element, which is particularly well suited for measuring shear strain that is generated on the surface of the shaft when the torque is applied.
To rewind slightly there, so the pressure sensor actually is kind of like using a mechanical element to put a load onto the source sensor to create the strain.
Yes.
So a little diaphragm or something?
Absolutely. Right. That's right. We have a diaphragm which presses upon the SAW device, deforms it, and changes the frequency of one of the resonators.
Yeah.
There are in total 3 resonators inside.
Mm-hmm.
This is not one possible approach. Other approaches can also be used. For instance, to achieve a good high pressure sensitivity, we could have etched the thin diaphragm in the SAW substrate.
Okay.
But at the time when we did all this development, etching a diaphragm in quartz was not a standard operation. So to keep the cost of the source sensing element low enough and acceptable for automotive applications, we decided to use mechanical transducer that converts pressure into deformation of the source sensing element.
And I guess, so I'm just thinking about that, probably the advantage of doing that is in most pressure sensors you would have a diaphragm again, but typically, to be sort of guaranteed that it's completely hermetic is quite difficult. And if the diaphragm ever breaks in service, you might have a leak, and sort of issues can come from that. But with the saw device, you can have the full saw unit on one side in the pressure area, and then all of the electronics and the reading stuff outside in the non-pressure area. And if the diaphragm fails or there's an issue, it doesn't matter. There's never ever any possibility of a leakage or sort of failure from that unit.
Well, I wouldn't say so.
Okay, right, okay.
Well, the point is that the saw device in our TPMS sensor is enclosed inside the fully hermetic metal package.
Yeah, okay, yeah.
So the hermeticity of that metal package is still important.
Yeah.
Because we measure actually the difference between the outside pressure and the pressure of the air inside that cavity.
Right, okay.
So that the hermeticity is still important. But providing hermetic seal is not that difficult, because we just laser weld the diaphragm to the metal base.
Right, okay.
Holding the saw device, so that it's all hermetically sealed.
Yeah.
In a very nice way.
Okay. And as a tire pressure sensor, what benefit does that bring? Well,
the main benefit is that it's a batteryless sensor. It doesn't require a battery. But the currently dominating technology in TPMS is battery-powered telemetry transmitters. So, and it does dominate everything, and at the moment it's not feasible to sort of commercialize TPMS sensor for passenger cars. For some time, one of our licensees manufactured this kind of sensing systems for motorsport.
I guess on a passenger car, with the batteries last, as long as the tire lasts, sort of thing. So people,
yes,
there's an opportunity to replace the batteries when tires are changed and things. So the durability, life cycles, not all that critical.
Yes, that's right. For motorsport, it's critical to have as small weight of the sensor as possible, and also our sensor allows to read the pressure every millisecond, or every 10 milliseconds to be more exact.
Yeah.
While the passenger car TPMS sensor transmits the pressure information and temperature information once, every 10 seconds.
So you get very high, very high
Update
frequency
rate.
measurement, lots of data. Yeah.
Yes.
Yeah. So in some applications, I can imagine that would be really important, and having that extra sort of level of data and durability would be an advantage, but not so much in the passenger car field.
No.
Okay, interesting.
Yeah, well, that's the current situation with TPMS. But Transense as a company is more focused now on torque measurement, and temperature measurement.
Yeah.
And originally we developed this sensing element for electrical power assisted steering system, for EPAS.
Moving on then to torque sensing.
Yes.
Yeah.
So, as I said, the torque sensing element was originally developed for EPAS, for electrical power assisted system. But obviously, we can measure torque applied not only to steering shafts, but also to any other shafts, starting from relatively small input gearbox shafts for sports cars to quite big shafts of industrial gearboxes, or wind turbines, or marine prop shafts.
Yeah. It's interesting because torque, quite often in a development environment, we spend a lot of time and effort very accurately, or as accurate as we think we can do, measuring torque to validate a product and sort of validate a design for a system. But there aren't many applications where we're able to embed a torque sensor into the product when it's gone into production using traditional technology. Like it's quite difficult to do, and not all that common. But it seems like the Transense technology allows you to do that potentially.
Yes, from the very beginning, from the point when Transense was founded as a company, the aim was to develop some torque sensor that could be used in high volume applications in production units rather than just for testing purposes.
Yeah. And I guess power steering, the EPAS unit is one example where, today there's a few different ways of doing it, but measuring the torque is necessary. So that is an active field of development. The one thing that it sticks out on the EPAS, obviously it's very safety critical. So you want that steering system to be completely robust, reliable. Was that a challenge?
Yes, definitely it is a challenge. Currently, the torque sensor which is used for EPAS is often based on a so-called torsion bar,
right?
That makes the shaft torsionally compliant.
Okay.
To increase the twist angle.
Yeah.
Because traditional sensors based on Hall effect, or based on optical measurements, they measure the twist angle.
Okay.
And in order to make this device safe, quite a tricky mechanical design of the shaft is used.
Well, and actually even sometimes, so that twist is something that you need enough twist that you can measure, but not so much that the driver can feel it or it introduces any kind of vagueness into the steering system.
Yes.
It's very challenging.
Yes, it is. What advantage does the torque sensor give us? The torque sensor based on SAW resonators happens to have the strain resolution, an order of magnitude higher than the typical strain resolution of a traditional thin film strain gauge.
Okay.
As a result, we can build a torque sensor for EPAS on a stiff shaft.
Okay, right.
So our torque sensor for EPAS is non-compliant at all, which is an advantage for certain types of vehicles, for instance, of the road vehicles.
Where they're seeing very high impact loads on the steering. Yeah, I think heavy-duty commercial vehicles as well. That kind of application, yeah. Oh, really? That's interesting, yeah.
Yes, and the fact that we can measure pretty small values of strain helps us to achieve sufficient safety factor for the steering shafts. And obviously the shaft design itself is quite simple. So that's one advantage. Obviously, another advantage is that it's a batteryless sensor, doesn't require any active electronics on the shaft, so that there is no need for changing the batteries or providing expensive devices for power transfer to the shaft. Doesn't require any rebalancing after instrumentation. Since the SAW device is very, very light, it can work at rotation speeds up to and above 20,000 RPM.
Okay.
One of our licensees uses SAW sensors or torque sensors on the shafts of avionic turbine engines, where the rotation speed is pretty high. And this sensor that we developed can work within the temperature range from -40 to +150 degrees centigrade and provides the accuracy better than 1% within the whole range.
So it not only are you able to get a very high sampling frequency out of it, so you can get a lot of data resolution, which for steering or propulsion I would think would be essential, but you're also able to do it very accurately as well. So you know that number that you're getting is a solid number. You can yes. really rely on that. So from a system control point of view, that's going to be critical.
Yes, that's right. Well, as we discussed before, it's totally insensitive to magnetic fields.
Yeah.
And you mentioned the high update rate. Yes, it is our standard reader provides the update rate of 6.7 kilohertz,
Okay.
which is sufficient for most of industrial and automotive applications.
Yeah.
And
Just about sufficient. Yeah.
yes, well, it
Yeah.
allows us to monitor quite fast torsional vibrations as well.
Yeah. Well, and you know, one of the challenges that I've certainly seen in the past designing control systems in vehicles is actually you end up having to do so much signal processing, filtering to take out noise that you really can't. You actually, there's a fine balance between seeing noise in the system and getting false readings and getting valid, useful data out, and you know you end up at quite a slow measurement rate because of that. So you have to be quite careful, but you're not going to hit that problem with the SAW device. You're just able to get such a quality stream of data coming out that you really could you could actively you could use that in an active control loop, for example. Which
that's right. Well, basically the EPAS sensors are used in the feedback control loop indeed.
Yeah.
Yes, and also they can be used for condition monitoring of various systems.
Yeah.
And they provide lots of information. It's a big question how to extract the most informative parameters from the torque signal, because obviously we can't keep transmitting this stream of torque values. So but that's more about the condition monitoring algorithms. We can provide enough information for condition monitoring systems.
Because you'd be able to detect quite a lot of things going on in there. So like premature bearing failures, or because you'd have a vibration signature off that, but you'd also potentially have things going on with system torque because of the extra friction that you could detect as well.
Yes.
Okay.
Although Transense is mainly involved in torque measurements, our wireless source strain sensing elements can also be used for non-contact measurement of axial load, and bending and bending vibrations if needed.
Yeah.
So that's the situation.
What do you think about? So my particular area of interest is around electric motors, and I've looked at this. I think, really in the past, getting like a temperature reading off the rotor of a motor would have been quite helpful. It's quite difficult to get into the rotor normally. Do you think it would be possible to use a SAW sensor to get a rotor temperature reading?
Definitely. As I mentioned before, the temperature reading comes as a byproduct of the temperature-independent measurement of torque.
Yeah.
So that our reader provides information about the torque and temperature within one packet.
And if we had a motor, if you think of it like normally you have the rotor on a shaft, could the sensor be quite close to the rotor, or does it have to space it away to get a good torque measurement?
Well, the only limitation is that the position of the sensor should be in the place where the strain does represent applied torque. So that's the only limitation. How close we can position the sensor to winding doesn't matter.
Yeah.
It can be as close as the mechanical design allows. But we need to place the sensor where the strain is linearly depends on the applied torque.
Okay.
Or proportional to torque.
You'd have to examine the shaft and make sure you correctly placed it, but as long as it was on the shaft and that all agreed, then so you could definitely measure temperature on the shaft at the very least, which would give you a good indication of the rotor temperature.
Yes.
It's from a torque measurement point of view. You're doing that with always with differential strain. So do you always have to sort of look at what's happening strain-wise on either side of the shaft, or?
Not always.
Okay.
Usually we install two sensing elements on two opposite sides of the shaft. The main reason for doing this is to cancel the influence of potential bending moments that can be applied to the shaft together with torque. If we don't want those bending moments to sort of distort the value of strain, then we need to cancel this influence by averaging the readings coming from the two sensing elements.
Okay, so that's the only reason you have two.
Another potential reason could be some sort of degree of redundancy.
Right, yeah, okay. Because actually, I mean, a shaft sag in an electric motor is a known phenomenon, and I guess that it would be that kind of thing that, you know, bending strain would be those sorts of loads on the shaft. Okay.
Yes.
And one other thing. So in the motor system, we always have a speed and position sensor, because to control the motor, we need to know where it is, so we know when to fire the phasers to make it go. And is it possible with the RF coupler to do something along the lines of sort of speed position measurement in there as well?
Yes, it is possible, and it's actually being done for the EPAS sensor. The coupler that is used in that system is made on a standard PCB material, as I mentioned before. And the same rotor couple can also have a copper target.
Okay, yeah.
Which is working together with the coils positioned on the stator RF couple.
Yeah, yeah.
So this arrangement allows us to add a inductive absolute angular position sensor into the torque sensor, torque sensor, so that two devices will work together quite happily.
Yeah. So potentially, because the normal is some sort of Hall effect or optical, I guess, like in the EPAS system. So a Hall effect rotary encoder is quite a common thing, or optical less common. So we potentially could replace that rotary encoder with
the inductive angular position sensor.
Right. Okay.
And the accuracy will be around 1 degree.
Another, just again, sort of wondering, when an electric motor, when the phasers, you know, you're firing the phasers on the motor at quite high frequency. You've got a 3-phase motor. You sort of shove. Not quite like that, but it's an impulse reaction. Would you be able to sample the torque to the extent where, let's say, a phase was off or a phase was not quite right? Do you think you'd be able to measure that kind of torque imbalance in the system? Or?
Well, the only thing I can say is that when we developed a torque sensor for kinetic energy recovery system for Formula One.
Oh, okay. That's an interesting example.
The torque sensor was installed on a short shaft connecting the electric motor to the crankshaft of the IC engine.
Yeah.
And we were told by our customer what sort of maximum torque we can expect in this system. After the first testing, it was absolutely obvious that torque was at least doubled.
Right.
Because of a very, very short, sharp torque pulses that our sensor measured.
Right.
And we decided that these pulses actually come from the electric motor.
Okay.
Because there is no other way how they were not firing pulses of the IC engine.
Yeah. So we'd have a data stream where we could actually sort of basically verify down to a phase firing level, potentially, that the motor was working properly.
I hope, but it all depends on the frequency of those pulses.
Yeah. If it's in the right kind of domain. I guess, I mean, you got some quite high speed motors being used at 25,000 RPM machines. So you can imagine, depending on the pole pair combination, you'd be sort of firing those fairly quickly. But
yes. Well, in many cases, I think we should be able to resolve pulses. We can also resolve individual firing pulses of internal combustion engines.
Okay, right. Yes. So I think I just noticed we're kind of running out of time quite rapidly. So just to start to wrap up, then it's been really interesting. And actually, I mentioned at the start, I do some work with Transense, but we've not really had an opportunity to properly sit down and talk about what the sensor can do or can't do. So it's been absolutely fascinating. Thank you for your time and for explaining it so wonderfully. It's helped me and I'm sure helped the listeners understand a bit more about SAW sensor technology and what you can do and what you can't do with it. Just to sort of close up, a question I basically always ask people is, looking at the business and the market and your technology, what do you think? What do you think the trends are going to be over the next few years, and what are you kind of excited about? What's coming that's got you excited?
Well, I very much hope that we'll come to the point when we can say, yes, our sensor has found applications in the products which are being produced in not in hundreds, but in at least tens of thousands units per year, if not millions units per year. That would really excite me. Just the scale of application, that would be really great to come to that point.
Yeah. And does it feel like we're kind of getting there in after this long journey?
Well, I hope we are pretty close to it.
Yeah, brilliant. Okay. Thank you.
Thank you, Ryan, for the nice opportunity.
We'll close there for the day. So thank you very much for taking the time out to listen to the podcast. I really hope you enjoyed that. We've got loads of more exciting episodes coming on electric vehicle and autonomous vehicle technology, powertrain components and systems. So a number of episodes ready. Back to the usual format. So don't forget, if you're working in a really exciting field in electric and autonomous vehicles and you want to talk about what you're doing, you can get in touch with me. You can find out how to do that down in the show notes. This is one of the first episodes that we've recorded under the new brand, so you'll notice that as well. It's really exciting to be kind of relaunching under the new brand, so it's fantastic. So if you can make sure, if you've enjoyed this, hit like or hit subscribe depending on the platform you're on, and leave us a rating. It really helps to get the show in front of some more people as we build that audience and help to share this the knowledge and experience from the people that I'm talking to. So thanks again, and I really look forward to speaking to you again soon.